Right. Okay, so you have seen on quite a number of occasions I'm presenting on machines or industrial type equipment. So I thought I'd sort of just share how the architecture of some of the Python programs I use. So this is I've written this sort of in Python-ish type code, and it's also written around GPIO is some of the basis of the language. But it's really just the principle I'm showing you, not so much the code itself. The other thing is I'm always interested. If someone's got a better way of doing this, I'm acutely interested. But the concept is I've got a machine that's doing effectively parallel processes on a machine, and I'm not using threads in Python, because fundamentally I have no idea how threads, or no, I use threads, but I don't understand or don't have a way of controlling them. Whereas if I code a certain way, I've got full control. I can put priorities in. I understand what's happening, when it will happen, etc. So that's what this is about. So the objective, sort of my fundamental objective, is I want to code in Python. I mean, I could do it in C and compile the program, but I prefer to run it in Python under a Linux OS, and it's running a real-time machine. But more importantly, I actually understand how these parallel processes are operating, and I'm conscious that Linux or anything with an operating system is going to, from time to time, take away control from say the Python program and to do its own thing. But I'm aware of that, and I just need to be able to take care of that. So I think the important thing about a machine is it's got inertia. It doesn't change instantly. So even things like valves and solenoids, or even little circuit board relays, they've all got a time constant of something like 10 milliseconds or more. So you can actually use that to your advantage. So I really only need some software or a control loop that will change, or it doesn't need to change more than every 10 milliseconds, and quite a lot of times not even every 100 milliseconds. That'll be fast enough to change the output state of a valve or a relay. So keeping that in mind, that can simplify the sort of the fundamentals of the software. So let's explain this, and I've got some examples here. So let's take, say, two push buttons, and each one operates a light. So you push the first button and it illuminates the first light for 10 seconds. You push the second button, it illuminates the second light for 10 seconds. And so there'll be two effectively independent processes. You should be able to press them, one after the other, and they both come on for 10 seconds. So if I've written up some, I'm calling them, press button 1, PB1, and LED1, and PB2 and LED2. And so if I write just a typical loop, I'd say, while true. So if you've pressed, so pi.read PB1, that's a piece of PyGPO sort of a syntax. So if you've pressed press button 1, turn on the LED, wait 10 seconds, turn off the LED. Then similarly if you press button 2, turn on the LED, number 2, wait 10 seconds and turn it off. And of course you can see there that with the time.sleep, as soon as you press the first button, the LED comes on, LED1 comes on, but the whole program effectively freezes at that point, and it just completely ignores press button 2 until the first LED that timer had timed out. So I can't get parallel processing with with that sort of way of structuring the programs. So the way I get around that is I go this way. I run a loop and I look at the time and I say, you know, and I call it loop time now. I read the time and I look at the time now and take away the time that I last went around this loop and say, if it's more than 0.01 seconds, 10 milliseconds, then do this operation. If not, just keep going around that if loop. So I execute this code once every 10 milliseconds, or once every 20 milliseconds, or once every 100 milliseconds, whatever I set that timer to. I set this this number here. And so 10 milliseconds is something I use quite a lot. So then I just update the loop time last. Then I do these operations. I'll read all the inputs, I'll perform the logic, and then I'll write all the outputs. Now that structurally has a real advantage is I'm not changing the outputs halfway through the logic, because historically, in relay logic, we had electromechanical relays. You'd have this concept called sort of race logic, where things were changing on the run, and in doing so, it screwed up your logic calculations. So a lot of industrial PLCs work this way, where they'll read all the inputs in a slab, perform the calcs, and then write the outputs. Now, it's not so evident here when I'm showing reading individual GPIOs, but when my IO cards, where I've got these sorts of things here, where I've got 8 inputs and 8 outputs, and I'm actually coming in through the I2C bus, a single read instruction actually reads in 8 bits, reads actually in 8 inputs in one instruction. So this idea of reading eight inputs in one instruction fits into this logic too. I just read all the each card here. Each card's got 8 inputs. So if I've got 3 cards, I just do 3 read instructions, perform all the calculations, and then do 3 write instructions. So it might be a bit small, but so what I'm doing here, I'm saying, okay, so it's the same architecture. Read the time. If the loop is now, it's more than 10 milliseconds more than since you operated last, execute. So then I say, read the input button, press button 1, and if it's true, it's been pressed right now, turn on a state. The LED 1.state equals true, and turn on the LED. If press button 2 has been pressed, turn on a Boolean state, LED 2 state equals true. So I'm just setting a Boolean register saying, is it true or not that the button's been pressed? And then I run some timer functions myself here. I'm not using time.sleep. I'm saying, if the state is true, if sort of halfway down here, if LED 1 state is true, then increment the timer by 1. Now, I know that I'm going around the sleep every 10 milliseconds, so 10 seconds is equal to 1,000 counts in this, it's effectively in this counter. So I say, if I've been around this loop 1,000 times, then set the LED state to false, turn off the LED, and reset the timer. And so I don't use the sleep function, because that's a blocking function. And I just do it with counters like that. Now, I don't use timers all that much. So, I don't see these time delays all that much. I'm doing a lot of other type logic. But it's the principle here that you go and test an input and set a state, set a Boolean register, and then test that as you go around this loop. So to take that concept of a state a bit further, so if we have two push buttons and each one operates a light, and you push button 1, it'll turn off number 2 light, and vice versa, you push number 2 button, it'll turn on number 2 light, but also turn off number 1. So what you've actually got is effectively 4 states here. So I'll go through them. So the concept of a state machine is you start looking at, say, your inputs or outputs, or you say your outputs, and define for each combination a state. So I'm saying both of them off state 0, LED 1 state 1, LED 2 is on state 2. And I'm also saying, this was not in the specification, they're both on. That's not something I want to happen, but I'm saying that's state 3. Since there's 2 variables, it gives you 4 different states. Oops. And then what I'll simply do is I'll start testing, how do I move between states? I'll say, if I'm in state 0, that's when both LEDs are off. I'll actually look at both press buttons 1 and 2. If I'm in state 1, that's LED 1 is on, I'll only just look at press button 2. So what this will start to do is completely simplify the logic, because I'm actually not interested in a whole, like in a machine, I'm not interested in looking at a whole stack of things. I could just focus in on one aspect. Once LED 1 is on, the only thing I'm interested in from then on is, has press button 2 been pressed? Of course, if you simplify the logic like this, you also simplify the amount of code that's got to, number of lines of code that are going to be processed each time we go in this loop. It also completely shortens up the time that it takes to go around the loop. So you ask the question, can I get around this loop in 10 milliseconds? The answer is yes, because you don't have to process all that much code for each loop. You're only processing the relevant bit of code. So if I'm in state 2, which is LED 2 is on, I'm only interested in is press button 1 being pressed. And then you also do all the illegal states. Well, what happens if I got myself into state 3? Both LEDs came on. No idea how I got there, but just in case I get there. Well, if that's the case, I say, okay, well, I'm going to go back to, I've made a decision here. I'm going to go back to state 0. I'm going to turn off both LEDs. Now, but I could do anything there. I could go to either state. It's quite often you see people who've got machines and they do weird things and they say, I have no idea how that's happened. It's impossible for that to happen. Typically, they've not taken care of all these illegal states because they're too optimistic about the skill of their own programming. So you start to draw out a state diagram like this, where you draw out for each of these states. On one side, or down the middle, I've drawn out the state numbers, and then in these arrows, I've drawn how you get from one state to the other. And then on the right-hand side, I've actually drawn out what the outputs are in each of these states. So this is the fundamental drawing that I would do for any machine that helps me work out what the states are, how do I get from one to the other. This is the logic diagram for me. And then to code that, I simply do this. Here's my loop again. Is the loop time now minus the time we went around the last one, more than 10 milliseconds. And then I just start saying, if I'm in state, if the state variable is 0, turn off both LEDs. So if the first press button has been pressed, state equals 1. So I've just changed the state number. So that as this processes around now, as the logic flows down here, it gets to this next if statement and says if state equals 1, which it is now because someone pressed the first press button. This bit of code here operates, and it basically turns on the first LED, turns off the second LED, and now looks for the second press button. and says, oh, if that's been pressed, go to state 2. And this will just process around, and if it'll only one of these blocks of code will actually be processed each loop. So I can have thousands of lines of code, but typically each loop may only be processing 10, 20, 30 lines of code. Hence I can get around these loops pretty quick. So that's a sort of a non-blocking piece of code. And I'm just going to return back to here where I said I would write this as read inputs, perform the logic, and set the outputs. Because the way I've written this piece here is not in that format yet. You'll notice I'm actually testing the logic here and writing the outputs combined. I haven't truly separated that out. So to do that, I would then just rearrange this a bit. So I set myself a section here where I read the inputs, and I read an input and set a Boolean variable equal to the current input. And this looks a bit odd when you're dealing with GPIOs directly, but it's far more sensible when you're actually reading off an I2C port and you're reading eight inputs in a block. You do some bit logic here to actually separate out each of the bits. And then I process the logic, same thing, state 0, do this, state 1, do that, process state 2. And I'm just looking in each of these, I'm looking at the state of the push buttons. And then over the page, I then set the outputs. So I've broken this code into those 3 blocks. So it's a little bit more testing, and it doesn't look as efficient, but that's only a factor of using, I'm just doing individual GPIOs here. So that's fundamentally that's the fundamental architecture I use behind, machines, etc. And what I can do then, I take the next step is when I'm doing the outputs, I might be writing physical outputs. I might be updating the screen, using say Pygame or something like that. I might be writing to a database. I might be doing a whole series of things in the outputs. What I'll do then is I'll look at the most important things and do them every loop. And if I'm just updating the screen, I really don't need to update that every 10 milliseconds. Probably every half a second is enough. So right back at the start up here, where I'm going around this loop, I just put a loop counter in here, and I'll count that up to say 1,000. That will give me a second, count a second. And I will only update the screen when that loop counter gets to 500, and then just reset it, and then that gets to 500 again. And that way I only do certain operations every half a second. And I'll start doing things like this time around the loop, update this part of the screen. So when it gets to 500, the next time around the loop, it gets to 501, I do another part of the screen. And I separate out the workload for the non-critical functions. Things like writing a machine status to a database where I can remotely monitor a machine, etc. I might only do that every 10 seconds or every minute. So I'll have a very large count number there. So again, I don't need to do everything, every loop. Whereas inputs and outputs and driving servo motors and VF drives and things like that, I do them every 10 milliseconds. So it seems to me to work quite effectively, this concept. Anyway, that's as simple as that. Anybody, any questions?
That was really interesting. Thank you. some couple of things occurred to me as you were talking there, and I suppose a lot of it depends on how complex you go. But I actually have two projects in sort of my own backlog that I've done that do this in two different ways, and one of them uses a state machine. That's one I wrote in C++, to run this slow cooker I sort of automated. And again, that uses the state machine concept to handle, there's several buttons to press, and there's hundreds of, probably tens of thousands of states, because there's states on states, for different things. And what I found effective for that was to use it. That truly was a state machine, like you described, but it saved states of things separately according to what they were. So, for example, I had a button class, and that button class could be initialized for a given button, like say the up button and the set button, initialized with what it did when you held it down constantly, how long the software debouncing was, how long to start something running when it was pressed, anything like this. And then all of that information is saved within that object. So all you have to do is just consult the object and say, hey, do you want to do anything? What I'm doing, I won't talk about this in my talk later, but the project that I will cover later is in Python and uses, I wrote event objects basically. So I'd say if you're doing something where, especially where the states are quasi-independent, so you can get very complex if you want to consider each one as an individual state, because there might be many. But like you said, maybe there's three buttons and they each have an LED, and each one wants to be on for 10 seconds when you press it, regardless of what the others are doing. In that case, I might suggest having an event class that records when it was pressed and on its own calculates when the light should turn off. Let me know when you can hear me. Someone thumb up or something. Yes, you can. Okay. Sorry, quick battery change. Yeah. So then you can have 10 events. Let's say you've got an event class which is button 1, and when you initialize button 1, you said, hey, what I want you to do is turn on LED 1. So you pass it a callback as its action, callback action, for 10 seconds. And so when you say button 1, you go button 1.pressed when you find that GPIO pin says it was pressed. And then every loop, you just go through all your events and say execute. And the event knows when it needs to be pressed. It checks the time. It says it's not time yet. It's not time yet. It's not time yet. It's not time yet. And when it is time, just calls the callback. In that way, your code is infinitely expandable. You can do this for thousands of states and buttons, whether they're interdependent or not. It's doing an absolute minimum each loop, and you can have the loops with a delay or not with a delay. It's up to you. And it's very readable as well, because for each one you can go, event.execute. That's what's happened. It's got a name. It's button 1. It's turning on this LED. It's done it, and so on. Yeah. It's an idea.
Yeah. So I've got a number of, like you're saying, I've got a number of programs which are purely event driven, or highly event driven. I've also got other programs where we're controlling machine speed, where it's actually effectively a PID loop. It's the number of events, like you press the start button and you won't have another button pressed to another event, if you like, for another 12 hours. In the meantime, it's actually the machine monitoring itself and monitoring analog inputs, etc., and varying. So there's this dilemma in that case. And the other thing is I've got to write this stuff for not just for myself, but for other people of all different categories of skill level, who can look after these machines as well. And the dilemma I have is writing classes like that, or just writing classes is can someone actually follow it? It's a challenge at times.
You're totally right in terms of setting up. It requires a higher level. But I would say if you're able to set up the class system, it's a lot more intuitive to say, hey, this is how you call it. That you tell it, this is what you do when you're done. This is how long you run for. And now it's easy, and then it's readable to anyone. They might not understand what a class is or whatever, but they can read it like English. Whereas if it's something like check if the time difference is more than 0.01, and then just do this 1,000 times, it's not immediately obvious that means wait 10 seconds until you really go down. You think, what's it going to,
Yeah, no, I agree.
I mean, one thing with the code as it is it suffers from Python lacking a switch statement. The good news is it lands in 3.1, 3.10. You finally get a match statement, so you can actually do cases, and everything looks a lot clearer rather than it just being, because ifs with the state machine make things just look like a sea of ifs, like you've just got really conditional on everything and you're really not sure what you're writing. So when that lands and everybody sort of updates their micropythons and things, that'll be quite nice to have. You're talking about other ways of handling it though. One thing I've done in the past with Python is actually stack functions. So if there are things to be done, you just have an array and you add a function to it for it to be done at the other side. So you can actually make decisions and stack up things to be done when you get at the other side, and then just execute them all sequentially in a nice clean moment. It's quite a nice little pattern to use with Python because you've got first class functions worth looking at.
Yeah.
And it's not utterly weird like objects.
Nothing weird about objects.
I'll say even without going to objects, there's one pattern which I always use instead of switch case, obviously, which isn't in Python yet, as you say, and that's just a dictionary. Just have a dictionary called state functions, where 1: execute state 1 is the function, and then in your code you don't have if, elif, lots of lines. You just do state functions brackets state, done. And you can also do one tiny thing. Enums make the states more readable. Otherwise, you have to think, oh, which state was state 12 again? And you have to go back and you go, oh, state 12 is when those two are on, but not those two. You can use an enum and give them all names. If state,
I'll give another hint is if you're doing numbered states, don't number them 1, 2, 3, 4. Number them 100, 200, 300, 400. Because when you go back and want to squeeze a state in, you can put it, you've got 100 spaces to put in another state.
Could I make a suggestion? I would actually go 2 squared for each of them. So you go 2, 4, 8.
That gets really hard
like that. But it is, but then you can do Boolean logic. So like if you want to have a state where it's all these 15 states at once, you can do that easily. It depends on what you need to do.
Sorry, Tony, I had a question. You mentioned real time, and obviously Python on top of Linux isn't going to be real time, but there must be some times when you do want some sort of supervision on it, or do you do anything like that, where you are supervising to make sure you are getting, say, 10 milliseconds or whatever you think you need to be getting? Like you put exceptions in if you sort of drift from your ideal 10 milliseconds, or what do you do?
There's quite a lot of times. One reason for running at 10 milliseconds is, well, put this way, from experience, you can run a lot of machines at 100 millisecond loops. And if you look at, say, top-end PLCs, you effectively can, in them, you can effectively run classes where each class will cycle in its own time. Well, it's effectively like threads, where each thread will cycle around, and you set some of them to 100 milliseconds, some to, say, 50 milliseconds, and say some to 10. So I simplify that in the way I do it. I just have one loop, say running at 10, but I know that it's not that critical if every now and then it skips one, and instead of doing 10 it did 20 milliseconds, or instead of doing 10 it stretched out to, say, 12 or 15. It wouldn't actually matter. So I'm not paranoid if the machine very occasionally. Now, what I typically do in development time is I'll actually record the times and just see how how close to the 10 it's running. If the loop's getting up at 9.5 milliseconds per loop, because just the volume of code, I'll start separating it out a bit. But I'm not particularly worried. But what I do put in is a Watchdog Timer. So if the machine, particularly if the code stops, it'll actually shut the machine down. So I've got an output that's cycling on and off, and if that stops, then it basically interrupts the emergency stop circuits and powers down the machine. But that covers a whole series of software failures, processor failure, power supply failures, everything. It will just pull up the machine real quick.
I used a similar pattern a year or two ago. I wrote an API to control in Python to control an X-ray generator, which had some given API, and obviously that's a safety critical piece of equipment. And again, exactly using watchdogs and callbacks, making sure that everything was followed up in the right way, and if not, hit a sort of software emergency stop.
Yeah, we're just building a machine at the moment to put cable on a drum, and the weight of that's probably ends up about a ton. So this thing spinning a ton of cable on a drum. You need to be able to pull that up pretty quick if you have a problem.
Hi Tony. Yeah, I think when I was doing embedded systems, I had a similar pattern to that. I think the only difference that I would say is that we used to do all the events as interrupts, which I don't know how you do that in Python, but kind of when you press a switch, that can happen anytime. And then we had a loop which would just sort of run through everything, and then it would just go back up to the top. So that's kind of similar to this pattern. My question is though, you didn't mention switch debounce. What's your approach to that?
So I use if I'm coming through GPIOs, I exclusively use PyGPIO, and it's got two features. One, it's got an interrupt, and secondly, it's got debounce, software debounce as part of the configuration files. So when you set the input or set the GPIO as an input, you set the debounce time. I use that a lot, and I use software interrupts on that. So in fact, if I'm measuring distance where I'm getting a pulse every now and then, but I don't. So I've got a wheel that's it's spinning, and I want to actually count the number of wheel rotations. I'll put a sensor on that, and I'll fire that straight back into a GPIO with an interrupt and a debounce on that.
Okay, makes sense.
If I'm coming in through an I2C port, I'm tending to actually get hardware debounce on I put an RC filter on the front end of the chips. I've got enough. Everything I do in industrial, I've got everything's optocouple connected, and I'll put an RC filter on that and just put a very short delay. And then if I really get a problem where the machine is mechanically, the state is changing backwards and forwards, and it may not be just the switch that's it's bouncing. It could well be the machine state is takes some time to change from one to the other. I'll put a loop in there and put some software debounce in, but I'll code that in specifically, and that could be quite long. That could be half a second, or quite often I'll do is I'll put a timer and I'll say I want to see it. So many, like I want to see it for half a second, but it cannot have reset in that time. So I'll think through what the logic is I need and then code it accordingly.
Okay, cool.
But I'm a strong advocate of PyGPIO, I can tell you. Yeah. Richard, you're muted. I think you're muted, Richard.
Hi, can I try again?
Yeah,
Tony,
sorry.
what's distinctive about your code to me is that rather than trying to run a code, execute code by a certain time, you're trying to execute code at a certain time. Do you know what this class of approach is called? Because it's been difficult to look up.
Not really. No, I'm not sure. No, I don't have a name for that.
I found it really difficult to search for that kind of thing. It seems as though the web's flooded with executing by a deadline. Anybody got any ideas on this executing at a time?
Isn't it simply event-based logic? Is that
I would describe this as just a state machine. I wouldn't even say it's event based.
right?
Yeah.
But yeah,
The only thing. The only thing you might say is that the event is the event is just time. A tick on the time clock.
But it's more than that, though, isn't it, Tony? Because it's not just on time; it's on whether the button is pressed, which is an event.
Yes. Yeah.
Yeah, but an event would typically come in on an interrupt because it would interrupt the flow of programming. This is one of the reasons why on MicroPython, for example, interrupts are not handled because you can't interrupt Python's event loop, because Python runs the event loop. You cannot come in at any time and say, yes, I want to change things. So you have to have various hacks to get around it. So it's, if you're aiming for a particular time or by a particular time, we're talking about deadline scheduling, where you actually set a deadline for something to be executed. But that's very hard work because you have to work out how long your thing is going to take before you know when to start it.
And it's an analog for deadline that I'm looking for, but for the case of at a particular time.
I mean, the other thing is you tend to code these things depending on the machine at hand. You've got to understand what the machine's doing and what's critical and what's not critical, and then code accordingly.
Must be interesting if things go wrong. Remember, had a machine go wrong, and when I was working in a factory, and it went a bit shaky on me. It was shaking dust from the rafters, causing a bit of commotion. It was a one-ton table that we had moving, so it caused quite a stir.
Yeah.
Thanks very much, Tony. Gonna move on. Thanks a lot. This is really good. Lots of good discussion there.
I was just going to say, I've actually seen kind of timing done in microprocessors using some quite clever stuff. It uses a timer interrupt that gets interrupted at set intervals. And all it does is it counts down on a number of different memory locations. So, for example, it might fire 100 times a second, but it has a 10 cycle counter. And then once that cycle's done, it decrements a whole bunch of other counters down by one each time. And so what would happen is the main application code would set something to like, say, preloaded with 6 seconds. And then this timer, interrupt timer that ran at regular intervals, would slowly decrement that over those 6 seconds. So that was really an effective way of doing it where you couldn't afford to have the blocking element. Because it had to do other things. So it's some quite, it's just so many different ways you can approach a similar kind of problem for different purposes. Sorry, you say you're going to move on. Sorry.
Thanks very much, Tony. Thanks, guys, for all those questions.